Summary statistics are definitely useful for describing an association, but it's also important that we keep in mind how little changes to the data set can affect these values. So one thing to keep in mind is that the slope depends on units. So when we talk about the slope, that's the predicted change in y in whatever units you're using for the response for a 1 unit change in x. So if we were to convert size to square meters, let's think about how a 1 unit increase in x would mean something different now. So if we're using square meters instead of square feet, then a 1 unit increase in x is much bigger than it would have been before, right? Because we know that 1 square meter is much larger than 1 square foot. So if you're making a bigger increase in your explanatory variable, a bigger increase in the size of the house, then this is going to lead to a bigger change in the price. So since that's our interpretation of the slope, that means that our slope would increase. And if we wanted to confirm that in the data, we could actually make a new column that looks at things in terms of the square meters. So I'm just going to do new column, and instead of calling this one square feet, I'll call it square meters. And I'm going to go to column properties and make a formula. So this is very similar to like what you would do in Excel. So the formula for the size in square meters is going to be the size in square feet times the conversion factor, so 0.0929. And then I'll just click OK, and OK again. And now I have a new column. I've got the square meters, and I can do analyze fit y by x with that explanatory variable, just like I did before. And let's compare that side by side to our original analysis. So you'll notice that the shape of the data looks the same. The only thing that has changed here is the scale. And the slope is much larger than before, and that's because a 1 square meter increase is a much more substantial change than a 1 square foot increase. Correlation, R-squared, and the regression line, these are all sensitive to outliers or unusual observations. So let's think about a couple different outliers and how they would affect things. So what if we added a house that had 2,300 square feet and it sold for $850,000? So here's our new point up here. So it's kind of in the middle, just above the rest of the data set. This is kind of an expensive house. So it hasn't really changed the slope all that much if we look at the slope of the line, and that's because it's really just pulling it straight up from the middle. If you think about the regression line is sort of trying to match the data, it's going to get pulled up a little bit. You notice that the intercept is not as small as it was before because of how it's gotten pulled up. Also, you'll notice that the R-squared has gotten smaller. And remember, R-squared is about how close the data values are falling to the regression line. So now that we've added this extra point that's kind of far away from the regression line, our R-squared has gotten smaller. So for this point, the slope changes just a little. And that's pretty common when you add a point kind of in the middle of your x values, and our R-squared goes down. And that's just because our new house, the new data point that we're adding, is far from the regression line. So this is sort of introducing some unexplained variability. Now let's think about a different kind of outlier. Let's think about a house that's really small, 884 square feet, so all the way to the left here on the line, but very expensive, $850,000. How would this change the regression? So this house is 884 square feet, but we're still sticking with that same high price. So I can see my new data value there. And this one actually has a much more dramatic impact. So it's pulling up on the far edge here, so it kind of has a lot of leverage, and that ends up making our line a good bit flatter. So remember, the slope before was like 212 square feet. It's all the way down to 111. This is a huge change in the slope. And because we've changed where the line falls, it's not as good of a fit for the data points anymore. So we also have a huge change in our R-squared. So with the old line, it was explaining like 45% of the variability. Now we're down to 12 because this line really isn't serving us very well after that outlier pulled it out of place. So when you have a value like this that is extreme on the x-axis, this was a really small house. If it's extreme on the x-axis, we call that an influential point. And you can sort of think about it like if you're pulling on the ends of something, pulling or pushing on the ends, you're going to have a lot more leverage than if you're pushing closer to the middle. So this ended up having a big impact on the slope. The slope was much smaller, I'll say much flatter than before, just to make it clear what that change means. And also our r squared goes way down. And really the reason for this is that the line doesn't fit well anymore. Okay, I'm going to delete this house now. What if we looked at a restricted range of x values? So in other words, what if we only looked at the relationship between size and price for medium-sized houses? We deleted the smallest and the largest houses. So I don't have these in order, so I think I'm just going to do a filter real quick. So I'm going to go to rows and data filter. And I want to filter by square foot, so I just double clicked on that. I'm going to drag this line over so that I'm not including these few smallest houses, and I'll do the same thing on this other side, dragging it in so I'm not including the largest houses. So then I'm going to click include, and that means only the ones that are selected are going to be included. The smallest and the largest houses are going to be left out. So if we compare this to our original analysis, we basically just zoomed in on this part, maybe between 1,500 and 3,000 square feet. We've zoomed in and we're just looking at those medium-sized houses. So after zooming in like this, I mean, the points seem kind of all over the place. It doesn't seem like there's a real strong relationship. And if we fit our line to that, we can see, yeah, the slope ends up being a lot flatter than before, and the r squared is very low, so only explaining about 3% of the variability here. So this actually happens in general. The correlation, the relationship between your variables tends to be much weaker if you're just looking at a restricted range. So it tends to be weaker over a narrow x range. And our last warning here is that we want to avoid making predictions about individuals based on group summaries. So we do that, that's called an ecological fallacy. So this example is looking at the relationship between the percentage of state residents that are foreign-born and the income of the state. So this is the percentage of state households that are over $100,000. Notice that both of these variables are describing the states. And if we look at this graph, each dot here is not an individual person, each dot is a state. So that means that it's reasonable to describe the relationship at the state level. So what we can say is that at the state level, there does seem to be a positive association, a positive relationship between the percentage of foreign-born residents, that's our explanatory variable, and the percentage of residents that make up more than $100,000. So all this is saying is that states that have a lot of immigrants who live there tend to also be states where a lot of rich people live. But that doesn't necessarily imply that the immigrants who live in the states are the ones making over $100,000. In fact, at the individual level, this isn't true. It turns out to be a slightly negative relationship. So if we were to look at this at the individual level, foreign-born people are actually slightly less likely to earn over $100,000. So we have to be really careful because the relationships that are true at the group level are not always going to be the same at the individual level.